Last video, we talked about the characteristic polynomial of a linear transformation and of a matrix. And now I want to talk about the minimal polynomial. So remember the setup from the beginning of this lecture. If we have V, a finite dimensional, let's say n-dimensional vector space over field F, and the linear transformation from V to itself, then the pair VT define an F bracket X module. And we've seen that we can apply the classification of finitely generated modules over a PID to this situation, and that there exists unique monic polynomials, a1 of x, a2 of x, up to am of x, each one having degree at least 1, and satisfying the divisibility relations a1 divides a2, a2 divides a3, and so on, up to am minus 1 divides am, such that V is isomorphic to the direct sum of cyclic F bracket X modules, F bracket X mod the ideal generated by A1, direct sum plus plus plus, F bracket X mod the ideal generated by AM. So V is this torsion F bracket X module, and there's this nice direct sum decomposition. And moreover, we know the annihilator of this F bracket X module is the ideal generated by AM, this largest invariant factor, the one that each of the other invariant factors divides. And this is the part that I want to zoom in on. So what does it mean for something to be in the annihilator of V? Well, remember, how does a polynomial act on V? Everywhere you see an x, you put in the linear transformation t. So what is am of x? It's the unique monic polynomial of minimum degree, such that if you put in t for x and apply this, you get some big polynomial expression in t, and that acts on V, that gives a linear transformation, and we want that to give the zero linear transformation. That we apply this to any vector in V, and we always get the zero vector. Okay, so this is a generator for the annihilator. If you have any polynomial that annihilates V, where you put in t for x and you get the zero linear transformation, then it's in this ideal generated by AM, which means AM divides that polynomial. So I'm going to give a definition, but we'll see sort of where it leads right after. So the unique monic polynomial that generates the ideal annihilator of V of F bracket X is the minimal polynomial of this linear transformation T, denoted MT of X. So this definition immediately leads from this observation right here, applying theorem 5, to the fact that the minimal polynomial of this linear transformation is am of x. It's the largest invariant factor of the decomposition of V in terms of these invariant factors, this direct sum of these cyclic F bracket X modules. So the idea is that you can define the minimal polynomial of a linear transformation before you know the classification of modules over a PID. So you can give this definition, and then applying theorem 5 from section 12.1 shows you what the minimal polynomial is, that it's this largest invariant factor. It's just that we haven't defined this before. So we get the definition and then a result that says what the minimal polynomial is. All right, so because we know that the other invariant factors all divide this largest one, we know that every invariant factor of V divides the minimal polynomial of this linear transformation T. So remember, when we're thinking about V as an F bracket X module, there's no reference to T here, but V only becomes an F bracket X module once we make a choice of a linear transformation. So here, the annihilator of V, this is V as an F bracket X module. So this depends on T. So that's why this still makes sense that this is called the minimal polynomial of T, even though T didn't appear earlier in this definition. Okay, so I'm going to pause and erase, and then we'll see some things that we know about the minimal polynomial. The next thing we'll do is discuss the connection between the minimal polynomial of a linear transformation and something about matrices representing that linear transformation. We know that there's an isomorphism between the ring of all n by n matrices with entries in F and the collection of all linear transformations from V to itself. So this is something we talked about in the section on the matrix of a linear transformation. You should see corollary 14 in section 11.2. And I'll let you think about the details here, but this means that if A is an n by n matrix with entries in F, it corresponds to some linear transformation. And we know for that linear transformation, there's a unique monic polynomial of smallest degree, so that you apply that polynomial to that linear transformation, and now you get the zero linear transformation. Using this isomorphism that comes from choosing a basis for V, there is also a unique monic polynomial of smallest degree corresponding to this matrix A. So this is called the minimal polynomial of A, denoted ma of x. And the defining property is you put A in for x everywhere, and you get the all zero matrix. Okay, so this also is not stated in Dominant Foot and proven this way, but I find it really helpful in thinking about minimal polynomials to work this out explicitly. So the thing I want to prove is that similar matrices have the same minimal polynomial. It's kind of similar to the argument we saw earlier that similar matrices have the same characteristic polynomial. And the idea is actually a little more general. It's just we're going to look at a polynomial and we're going to ask, what has to be true when you plug in a matrix for this indeterminate and get 0? So let's take any polynomial, f of x to be an x to the n plus a1 x to the 1 plus a0 x to the 0, where these ai's are just elements of our field f. What happens when you take p inverse ap and raise it to a power? So this is an n by n matrix. We can multiply it by itself k times. It's p inverse ap, p inverse ap, p inverse ap times k times. Now we can just use associativity to group the parentheses here. P inverse a times p inverse, which is the identity, times a times p inverse, times a times p inverse. All those p inverses are going to cancel out. We get a p inverse. We get k a's in a row. Then we get a p at the end. We get p inverse a to the k p. So now it's easy to apply this polynomial to this matrix. You get an p inverse a to the n p plus a1 p inverse a to the 1 p plus a0 should be times the identity matrix. And the tricky thing is to write it as p inverse times I, which is a to the 0 plus p. Why do we do it that way? Because now by the distributive law, this is p inverse times an a to the n plus a1 times the matrix a to the first power plus a0 times the identity matrix a to the 0th power times p, which is p inverse f of a p. P and p inverse are invertible matrices. So f of a is 0 if and only if f of p inverse ap is 0. So in particular, each of these matrices has this unique monic polynomial of smallest degree, such that you put in this matrix and you get 0, and those minimal polynomials are the same. Okay, so what are we seeing? You start with a linear transformation. You have a minimal polynomial. You choose a basis for this vector space V, and you get a matrix of that linear transformation with respect to this basis. You could change the basis. You get a whole bunch of different matrices, but they're all similar to each other. So all of those matrices have the same minimal polynomial. So what we're seeing is that the minimal polynomial of a linear transformation T is the minimal polynomial of a matrix A representing T with respect to any choice of basis. So you have the minimal polynomial of a linear transformation, choose a basis, you get a matrix. That linear transformation and that matrix have the same minimal polynomial no matter which basis you pick. So you may object that I'm doing something a little sneaky here, that I'm not explaining why when you choose one basis, the matrix that you get at the beginning has the same minimal polynomial as the minimal polynomial of the linear transformation. I'll let you think about the details. I think it will be helpful in the next video when we make a particularly nice choice of basis for this vector space V, where we'll get a particularly easy to understand matrix corresponding to that basis.